Welcome back to another deep dive. Today we're doing something a little bit different.
A little bit, yeah.
Usually when we sit down to talk about artificial intelligence or machine learning, the conversation, it always seems to drift towards the magic.
Oh, absolutely. The magic.
You know exactly what I mean. The wow moments. The chatbot that suddenly writes a perfect sonnet in the style of Shakespeare.
Or the image generator that just, hallucinates this incredible surrealist painting in, 10 seconds?
10 seconds, yeah. Or the self-driving car that somehow navigates a chaotic roundabout in rush hour. It just feels like this mysterious, opaque black box.
It does. It feels like you put data in one end, some kind of miracle happens inside, and then value just pours out the other side.
Exactly.
And, the media loves that narrative. It sells. But I always come back to that Arthur C. Clarke quote.
Any sufficiently advanced technology is indistinguishable from magic.
That's the one. And I think our job today is to handle that distinction. We're here to ruin the magic trick a little bit.
We are going to pull back the curtain.
We're pulling back the curtain. We're looking at the wires, the trapdoors, all the pulleys that make the magic happen.
I love that. We are looking at the blueprint, not just the code, but the actual architecture of how these systems are really built. And we're basing this deep dive on a document called N2, the Machine Learning Lifecycle, an architectural blueprint.
And that keyword there, I think, is architectural.
Architect's perspective. It's not a coder's perspective.
And that is the crucial distinction. That's everything, really.
So let's define our mission for today. If we're not talking about, sitting down and writing Python code, what are we talking about?
We're talking about the huge, massive gap between what you might call a science experiment and a real production system.
Okay.
Our mission is to get beyond this idea that machine learning is just writing an algorithm. We need to understand the whole end-to-end flow. We're going to trace the entire journey.
From the very beginning.
From the very beginning. From that vague idea in a conference room, hey, wouldn't it be cool if AI could stop fraud? All the way to a living, breathing system that's handling millions of requests a day without, and this is the important part, without crashing.
We're looking at the life cycle.
We were looking at the life cycle.
Yeah.
The whole thing.
I love that distinction because I think a lot of people, myself included sometimes, assume a data scientist and a machine learning architect are basically the same job.
They sound similar for sure.
Yeah. They both work with data. They both build models. But the source material, it suggests they have very different mindsets. How would you break that difference down?
It's a great place to start. And honestly, it's the reason so many projects fail. A data scientist is often like a specialized researcher, maybe a mathematician.
Yeah.
They're focused on the science part of it, finding the perfect algorithm, tweaking the math, getting the absolute highest accuracy score on a nice, clean, static data set.
They're looking at the trees.
They're looking at the trees. Sometimes they're looking at the veins on a single leaf. And that's incredibly important work, don't get me wrong. But the architect
is looking at the whole forest.
The whole forest. In fact, they're looking at the entire ecosystem. The soil, the weather, the supply chain for water. They ask totally different questions.
Like what?
Well, the data scientist asks, is this model accurate? The architect asks, okay, great, it's accurate. Now, how do we get data to it reliably at 3 a.m. on a Tuesday when the servers are under heavy load? How do we monitor it? How do we update it without taking the whole system down?
So if I can use an analogy, the data scientist is the master chef who invents an amazing new dish.
Yes, exactly.
But the architect is the one who designs the entire restaurant around it. The kitchen, the plumbing, the supply chain for the ingredients, the seating plan, the fire escapes, the waste disposal system.
That is a perfect analogy. Absolutely perfect. You can create the best souffle in the world, a Michelin star model. But if you can't get it to the customer's table before it collapses, it's useless.
Or if you run out of eggs after the first order because your supply chain is broken.
Then you don't have a business.
Yeah.
You just have a cool science experiment. And that right there is the central theme of this deep dive. It's not just about the algorithm. It is about the life cycle.
Okay, let's unpack this life cycle then. The source material breaks it down into 5 critical phases. Can you just give us the high-level roadmap before we dive into the details?
Absolutely. So think of it as a progression, but it's one that often loops back on itself. It's not always a straight line.
Right.
Phase 1 is design. That's all about business understanding. Phase 2 is data engineering, which is the real heavy lifting. Phase 3 is model development. That's the science experiment part we were just talking about.
The fun part.
The fun part for many, yes. Phase 4 is deployment, which is where it meets production reality. And finally, phase 5 is monitoring, which the source beautifully describes as fighting entropy.
Fighting entropy, I love that. It implies that the natural state of these systems is to drift into chaos.
It is. Without constant attention, they will.
Okay, let's start at the beginning. Phase 1, the design phase. Now, this seems a bit counterintuitive to me. If I want to build an AI, my first instinct is to open my laptop and start writing some Python.
And that would be the single most common mistake,
Uh-huh.
honestly. If you start by coding, you've probably already failed.
Really?
Yes, you have to start by defining what you are solving. This isn't about code. It's about business understanding. It's about problem framing.
And the source has a great example of this. You can't just go to your team and say, I want to stop fraud. It's too vague. A computer has no idea what that means.
Right. Stop fraud is a business desire. It's a goal. It's not a machine learning task. The architect's first job is to be a translator.
A translator from business speak to math speak.
Precisely. They have to convert stop fraud into something very specific like binary classification.
Binary classification.
Yeah.
Okay, that sounds technical, but it really just means putting things into one of two buckets, doesn't it?
That's all it is. Bucket A or bucket B. You look at a single specific transaction and you ask a yes or no question. Is this transaction fraud, which we'll call a 1, or is it normal, which we'll call a 0?
So you've narrowed the scope from this broad wish, stop fraud, to a very specific, solvable mathematical problem.
You have to. Otherwise, you're just lost.
Okay, so we framed the problem. We want to classify transactions. But then comes the next big question. How do we even measure success? And this is where it gets really interesting for me, because the source brings up this idea of metric selection. It's not just about accuracy.
No, accuracy can be incredibly misleading.
And it dives deep into the specific trade-off between something called precision and something called recall.
This is one of the most important conversations an architect will ever have with the business stakeholders. And it's not a technical conversation, not really. It's a value conversation. You have to decide together what a mistake looks like and what it costs.
So let's stick with our fraud example. Walk me through the trade-off. What's the battle between precision and recall there?
Okay, so let's imagine two different worlds, two different priorities. In scenario A, your absolute top priority is to catch every single instance of fraud. You never want a thief to get away with a single penny. You want to maximize your recall.
Okay, high recall. Catch all the bad guys. Sounds good so far.
It does. But to do that, your model is going to have to be very, very aggressive. It's going to be paranoid.
Paranoid.
Yeah, it's going to flag lots of transactions that look even a tiny bit suspicious, which means it's also going to flag a lot of transactions that are actually perfectly innocent.
So that's me at the grocery store buying a carton of milk, and my card gets declined because the AI thinks I'm a master criminal.
Exactly. That's a false positive.
Yeah.
And you're not just annoyed, you're embarrassed. You might even stop using that credit card. That has a real business cost.
Okay, I see the downside. So what's the alternative? Scenario B.
Scenario B is the opposite. Your top priority is to never, ever annoy a good customer. You want to make absolutely sure that when you flag a transaction as fraud, you are right. You want high precision,
So you're only flagging the slam dunk cases of fraud.
the ones you're 100% sure about. But the trade-off is, well, some of the clever thieves, the more subtle cases, they're going to slip through the cracks. You'll have fewer false positives, but more false negatives fraud you failed to catch.
So the architect's job is to go to the business and ask that really tough question. What is the cost of a wrong prediction?
Precisely. But even more specific than that, what costs more, annoying 1,000 good customers to catch one bad guy, or letting one bad guy slip through to keep 1,000 good customers happy?
There's no single right answer to that, is there? It depends on the business.
It completely depends. A high-end luxury brand might prioritize customer experience above all else. A high-volume, low-margin business might be more worried about the financial loss from fraud. You can tune the model either way, but you have to have that conversation before you write a single line of code.
That makes perfect sense. It's not just, is it accurate? It's, is it accurate in the way that actually matters to our business goals?
You've got it. That's the core of the design phase.
Okay, the last part of this design phase, according to the source, is the feasibility study. This feels like the cold water in the face moment, the reality check.
It's the sanity check. It's where the architect has to be the most skeptical person in the room. The question is brutally simple. Do we actually have the data to solve this problem?
And it's not just, do we have data?
No, not at all. You might want to predict the stock market. Great. Do you have decades of historical stock data? Maybe. But here's the kicker. Can you get that data in real time, in the milliseconds you need it to make a trade. If the answer is no, it's a non-starter.
The source phrases it as, is the data available historically and in real time? That seems like a simple question, but I bet it trips up a ton of projects.
All the time. It's
Yep.
the classic trap. A team builds a beautiful model using a historical data set. They download it as a CSV. It works great. Then they go to deploy it, and they ask the engineering team, okay, we need access to these 50 data points, live with less than 50 milliseconds of latency.
And the engineers just laugh.
They laugh or they cry. Because building that real-time data pipeline might be a year-long project in itself. You might have a beautiful archive of data from last year, but if you can't access today's data until tomorrow, you can't build a real-time fraud detector. You can only build a retrospective report.
Wow. So the feasibility study can kill a project before it even starts?
And it should.
Yeah.
It's better to kill a bad idea in the design phase than after a year of wasted effort.
Okay, so let's assume we've passed the sanity check. We've got a plan, we know what we're solving, we know the metrics, we have access to the data. Now I can finally move to phase 2, the data engineering phase.
The fun begins.
Well, the source drops a statistic here that's a little bit depressing for anyone who just wants to do the cool AI stuff. It says this phase is usually 60 to 80% of the actual work.
It is the unglamorous, inconvenient truth of the entire industry.
60 to 80%.
At least. Everyone wants to be the person tuning the neural network. No one wants to be the person cleaning messed up CSV files at 2 a.m. But the goal here is non-negotiable. You have to turn raw, messy, real-world data into a pristine, model-ready format. Without this phase, you have absolutely nothing. The fanciest algorithm in the world is useless.
So let's get into the nitty-gritty. It starts with ingestion. That's just bringing the data into our system, right? But the source outlines 2 very different ways to do this: batch and stream.
Right, and the choice between them has massive architectural implications. I like the analogy in the source. Think of it as the difference between getting a daily newspaper and watching a 24-hour news ticker.
Okay, I love that. Unpack that for us. Let's start with the newspaper with batch processing.
Batch processing is the newspaper. You're not concerned with what happened 5 minutes ago. You're concerned with what happened yesterday. You collect all the data that was generated over a fixed period, say the last 24 hours. You bundle it all up.
Into a big file, like a CSV or Parquet file.
Exactly. Parquet is very common for this. And then you process that entire batch all at once. Usually this happens overnight when system traffic is low. A scheduled job kicks off and just churns through that mountain of data.
And the source mentions tools like PySpark for this.
Yes, PySpark is the king of batch processing. It's a tool designed to handle massive amounts of data in a distributed way. It's perfect for things like generating daily reports or training models that only need to be updated once a day.
Okay, that's the newspaper. Now what about the news ticker? Stream processing.
The news ticker is a completely different beast. This is about reading data in real time as it arrives, event by event.
So every single time I swipe my credit card or click a link on a website or a sensor on a factory floor beeps.
That's an event. And that data flows instantly through the system. It's not collected and saved for later. It's processed on the fly.
And for this, the tools are different. We're looking at things like Kafka or Azure Event Hubs.
Exactly. Think of Kafka as a massive, high-speed, durable pipe. Producers, like the credit card processing system, are constantly writing messages into this pipe. And consumers, like our fraud detection model, are constantly reading from it in near real time.
And you need this if you want to make those instant decisions.
You have to have it. If you need to stop that fraudulent transaction while the customer is still standing at the register, a daily batch process is useless. You need streaming.
Okay, so we've got the data flowing in one way or another, but raw data is usually, well, it's a mess. It's gross.
It's always a mess.
It's got missing values, it's got typos, weird formatting. The source calls this part understanding the dirt.
Which is a great way to put it. This is exploratory data analysis, or ED. Before you do anything else, you have to just look at your data. You have to understand its shape, its quirks, its flaws.
What are you looking for?
Everything. You look at the distributions of values. Are there crazy outliers? If you have a column for age and someone has entered 999, you need to know that. Are there null values? How many? If 90% of a column is empty, it's probably not useful.
And then you have to fix it. This is the pre-processing step.
This is the cleanup. You fill in the nulls with a reasonable value, you cap the outliers, you use standardized text fields. But even more important is validating the schema.
What do you mean by that?
You need to set rules. The source mentions a fantastic tool called Great Expectations. And the name is perfect because that's what it does. It lets you define your expectations for the data.
Like a contract.
Exactly like a contract. You can say, I expect this age column to always be an integer between 0 and 120. Or, I expect this state column to never be empty and to only contain valid two-letter state codes.
And if new data arrives, that violates that contract.
The pipeline stops, it throws an error, it prevents that garbage data from ever reaching your model. It's the ultimate defense against the garbage in, garbage out problem.
Okay, this is critical. So once the data is clean and validated, we get to what the source calls making data smart. Feature engineering. This is where the real art comes in, isn't it?
It really is. This is where a good data scientist or architect can make a huge difference. Feature engineering is about creating new, more powerful variables from the raw data you have.
The raw data itself might not be enough for the model to learn from.
Often it's not. The example in the source is perfect.
Yeah.
A raw timestamp. To a computer, a timestamp like 2023-10-27-23.00000 is just a very large number. It doesn't inherently understand what that means in a human context.
So we have to transform it. We have to give it that content.
We transform it into a feature, or multiple features. From that one timestamp, you could create a feature called is nighttime, which is a simple yes or no, or day of week, or is weekend, or is holiday.
I see. And suddenly, the model can very easily learn a pattern like fraud is much more likely to happen on a weekend at night.
Exactly. You're giving the model a massive hint. You are translating the raw data into human logic that the machine can then process mathematically. You're making the data smarter.
And the source mentions specific tools for this, like the PySpark pipeline, vector assembler, and string indexer. These are the actual nuts and bolts that do that transformation.
Correct. These are tools in the data engineering toolkit that automate this process. A string indexer turns a text category like New York into a number, like 3. A vector assembler takes all your numeric features and bundles them into a single vector, which is the format most ML algorithms expect. A pipeline lets you chain all these steps together.
Now, here's a problem I hadn't even thought of. You go through all this work, you build these amazing features, you train your model, but then you have to use those same features in the real world when you're making live predictions. The source talks about feature management and the problem of consistency.
This is a classic nightmare. It has a name. Training serving skew.
Training serving skew. Okay.
Imagine you're building your model in a Python notebook. You calculate a feature like customer average spend last 30 days. You write some pandas code, it works. You train the model, great.
Okay.
Now you give that model to the production engineering team. They don't use Python. Their real-time application is written in Java or Go. So they have to re-implement the logic for that feature. And maybe they make a tiny mistake. Maybe they include today's spend in the average, but your training code didn't.
Oh, no. So the model was trained on one definition of average spend, but in the real world, it's being asked to make predictions based on a slightly different one.
And his predictions will be subtly wrong, or maybe disastrously wrong. The model is seeing data that doesn't look like what it was trained on. This skew is a silent killer of ML projects.
So how do you solve this? This seems incredibly difficult.
You solve it with a feature store. The source mentions tools like Feast, Tecton, or the Databricks feature store.
And what does a feature store actually do?
It acts as a single source of truth for your features. You define the feature's logic once. This is how we calculate average spend. And you check that definition into the store.
And then?
And then both your training pipeline and your real-time production system read from that same store. The training job asks the store, give me the average spend for all customers as of yesterday. The production app asks, give me the average spend for this one customer right now. But it's the same underlying data and logic. It guarantees consistency.
That seems absolutely critical for any serious system. Wow. Okay, there is one more concept in this data phase that the source flags as crucial, and that is point-in-time correctness. This sounds like we're getting into time travel.
It effectively is, and it's all about preventing the single most seductive error in machine learning. Data leakage.
Data leakage.
This is the most common way to build a model that looks like a work of genius in the lab, but fails completely and utterly in the real world.
Okay, give us the explain like I'm 5 version of this.
Okay. Imagine you're building a model to predict if a stock price will go up tomorrow. You're training your model on years of historical data. Now, if you accidentally include tomorrow's closing price in today's training data,
the model will just learn to look at the answer.
Exactly. It'll look at the answer key. It'll have 100% accuracy. You'll think you've invented a money printing machine.
But you've just taught it how to cheat. In the real world, you don't have tomorrow's closing price today.
You don't. That's data leakage. You've leaked information from the future into the past. Point-in-time correctness is the discipline of ensuring that when you build a training data set for a specific moment in the past, the data you use reflects only what the world looked like at that exact moment. You have to pretend you don't know what happened next.
So if I'm trying to predict if a customer will cancel their subscription in the month of June,
Yes.
I can't use any data about a support ticket they filed in July to make that June prediction.
Precisely. Because at the time of the prediction in June, that July support ticket hadn't happened yet. Using it is cheating. This is where feature stores are also incredibly helpful because they're often designed to let you query data as of a specific timestamp, which solves this problem.
That is fascinating. It's like having to enforce strict historical role-playing for your computers.
It is, and it's so easy to get wrong.
Okay, so to recap this massive phase, we've ingested the data, we've cleaned all the dirt out of it, we've engineered smart features, we've stored them in a central place to avoid skew, and we've made sure we're not cheating with time travel. Now can we finally get to the part everyone waits for, phase 3, the model development phase?
Yes, now we get to do the science experiment.
The source calls it the fun part, where the algorithm actually learns. But even here, it's not one size fits all. The world is divided into a few camps: classical ML, deep learning, and auto ML. Let's break those down.
Sure. So classical ML is your bread and butter. This is for your tabular data.
What's tabular data?
Anything that looks like a spreadsheet or a SQL table, rows and columns. If your data fits neatly into that structure, this is almost always where you should start.
And what are the standard tools of the trade here?
The Swiss Army knife that everyone learns first is scikit-learn. It's fantastic, easy to use, has everything you need to get started.
But if you need more firepower...
If you're chasing that last percentage point of accuracy or competing in a Kaggle competition, you're probably using XGBoost or LightGBM. They are gradient-boosted tree algorithms that are just incredibly powerful on tabular data.
And what if my data is massive, too big for one computer?
Then you turn to PySpark MLlib. It's designed to do this kind of classical ML, but distributed across a whole cluster of machines.
Okay, so that's for our spreadsheets. But what if our data isn't structured? What if we're dealing with images or audio files or just plain text?
Now you've entered the realm of deep learning. This is the domain of neural networks.
And who are the heavy hitters in this space?
There are two main giants. PyTorch is incredibly popular in the research community. It's known for its flexibility and Pythonic feel. It makes it easy to experiment with wild new ideas.
And the other giant?
TensorFlow, along with its high-level API keras. TensorFlow is often seen as the more production-ready, industry-standard choice. It's got a massive ecosystem built for deploying models at scale.
And the source also mentions Hugging Face specifically.
Yes, for anything involving text, especially the large language models we hear so much about, Hugging Face is the undisputed king. Their Transformers library has become the de facto standard.
Okay, and then there's this third category that sounds almost too good to be true. Auto ML. This sounds like the robot doing the data scientist's job for you.
It essentially is, to an extent. Tools like H2O.ai or Databricks AutoML take a brute force approach to the problem. You basically just point them at your dataset and say, find me the best model. They will then go and try dozens of different algorithms. A linear regression, a random forest, a neural network, and they'll try a bunch of different settings for each one. At the end, they spit out a leaderboard and say, hey, this XGBoost model with these specific settings worked best.
So it's great for getting a quick baseline result.
Exactly. It's a fantastic starting point.
Speaking of baselines, the source lists baseline first as a key best practice here. It says, always start with a dumb model. Why on earth would you want to start with a dumb model?
Because complexity is a liability. It's a cost. It's a maintenance burden.
So even if you know a neural network will probably be better.
I still start with something simple, like a logistic regression. Very basic math, it's fast to train, and it's easy to understand. If that simple model can solve your problem with, say, 90% accuracy, you have to ask yourself a hard question.
Is it worth it?
Is it really worth spending the next 3 months building a massive, complex deep learning network just to get to 91%? Is that 1% gain worth the cost of building, deploying, and maintaining that much more complex system? The answer is often no.
So prove you need the complex tool before you reach for it.
Beat the baseline. If your fancy model can't significantly beat the simple one, stick with the simple one. It's pragmatic engineering.
I like that. It's very grounded. Now, the training process itself, you're feeding data into a model. But there's also something called hyperparameter tuning. The source calls these the knobs on the model.
That's a great way to think about it. The model learns the parameters from the data, the weights and biases. But you, the human, have to set the hyperparameters, the settings for how it learns.
Give me an example.
In a random forest model, one hyperparameter is the number of trees in the forest. Another is the maximum depth of each tree. For a neural network, it's the learning rate. How fast should it adjust its weights? Tuning these knobs, finding the right combination, is how you squeeze out that last bit of performance from your model.
And once we've tuned it, we have to evaluate it. And this goes all the way back to the design phase. We're checking our chosen metrics, like precision and recall.
Right. And you have to do it on data the model has never, ever seen before. The test set.
Why is that so important?
Because if you test your model on the same data you trained it on, you're not testing its intelligence. You're just testing its memory. Of course it will do well. It's already seen the answers. You need to test it on new, unseen data to see if it can generalize what it learned.
That makes sense. Okay, there's one more set of tools mentioned in this phase that the source really emphasizes: experiment tracking. It mentions things like ML flow or weights and biases. Why is this so critical?
Because data science, true data science, is messy. It's not a straight line. You might run 50 different experiments in a single week.
What if I drop this column?
What if I tune this hyperparameter? What if I try XGBoost instead of late GBM? What if I use the data from last Tuesday? If you don't have a rigorous system for tracking every single one of those runs, what data you used, what version of the code, what parameters, what the final result was, you will completely lose your mind.
You'll find a great result and have absolutely no idea how to reproduce it.
It happens all the time. An experiment tracking tool is like a digital lab notebook for the data scientist. It automatically logs everything for you. It keeps you sane, and more importantly, it makes your work reproducible, which is the cornerstone of good science.
The source also mentions a tool called DVC here, data version control. How is that different from Git?
We use Git to version control our code. But what about the data itself? The data changes. DVC allows you to version control your actual data files, even massive ones. So you can reliably say, I want to rerun the exact experiment from last Friday. And it can pull not just the right code, but the exact version of the data set that was used. It's vital for that point-in-time correctness we talked about.
Wow. The level of discipline required is incredible. Okay, so we've done it. We have a model. It works on the test set. It beats our dumb baseline. It's all logged and reproducible in our experiment tracker. Now comes the really hard part, phase 4, the deployment phase.
Leaving the lab. This is where we separate the science experiments from the real production-grade systems.
The first step, according to the source, is the model registry. This sounds like more than just saving the file, right?
It's much more. A model registry, which is often part of a tool like MLflow, is a central version repository for your trained models. It's not just a file. It's the model plus all of its metadata.
Like what?
Which experiment created it, what its performance metrics were, who trained it, and most importantly, you can apply tags to it. You can tag a specific version of a model, say version 2.1, as staging or production. It's the official handoff point. It's the company saying, this model, this specific version, is the one we are now trusting with our business.
Okay, so the model is registered and blessed for production. Now we have to actually serve it. The source outlines 3 main strategies here, and it says the choice depends on latency and cost. Let's walk through them. First up, real-time API.
This is the one most people think of when they think of AI. It's also called online inference. You need an answer, and you need it right now.
The credit card swipe.
The credit card swipe is the perfect example. The request comes in, and within milliseconds, the source says usually less than 100 milliseconds, the system needs to return a decision, approve or decline.
What does the tech stack for that look like?
Typically, you wrap your model in a lightweight web server. In Python, Flask, or Fast API are extremely common for this. For higher performance, you might use a dedicated model server like TensorFlow Serving or NVIDIA's Triton Inference Server.
And where does this run?
You package it all up in a container and run it on infrastructure like Kubernetes.
And the big downside here?
The cost.
Yeah.
It's expensive. You have servers running 24/7 just sitting there, waiting for requests to come in. Even if no one swipes a credit card at 3 a.m., that server is on. It's consuming power, and you're paying for it.
Okay, that makes sense. So what's strategy number 2? Batch inference.
This is our newspaper again. This is for when you don't need an instant answer. Latency is not a concern.
Give me an example.
Let's say your streaming service. You want to generate personalized movie recommendations for all 50 million of your users. You don't need to do that in real time. You can run a big job overnight.
So you spin up a massive cluster of machines.
Exactly. Use a tool like PySpark or a workflow orchestrator like Airflow. The job starts, it scores all 50 million users, writes the results to a database, and then it shuts down.
And that's the key difference.
That's the key. It's much, much cheaper because you only pay for the compute while it's actually working. Once the job is done, you stop paying.
Okay. And the third strategy is a really interesting one, embedded or edge.
This is where you're not calling a server in the cloud at all. You're running the model directly on the device itself, on your iPhone, on an IoT sensor in a factory, maybe even in your car.
Why would you do that? What are the advantages?
Two huge ones: speed and privacy. Think about unlocking your phone with your face. You can't wait for the image of your face to be sent to a server in Virginia and then get a response back.
Yeah.
It has to happen instantly, right there on the phone. We're talking less than 10 milliseconds.
And privacy.
The data never leaves your device. Your face scan, your voice commands, they can be processed locally without ever being sent over the internet. Also, you might be in a place with no internet connection, like on a factory floor or a remote oil rig. The model has to work offline.
And the tools here are specialized things like TensorFlow Lite, ONNX Runtime, or Apple's Core ML.
Correct. These are special runtimes and formats designed to be very small and efficient, so they can run on processors with limited power and battery life.
Now, regardless of which of these three strategies we choose, the source has a very clear best practice rule. Always ship your models in Docker containers. We hear about Docker and containers all the time. Why is it basically non-negotiable in this world?
Because it solves the single most frustrating problem in software development.
Yeah.
The "it works on my machine" problem.
I've definitely said that a few times.
We all have. A machine learning model is incredibly sensitive to its environment. It depends on very specific versions of its libraries. Pandas version 1.2.3, TensorFlow version 2.4.1. If the production server has slightly different versions installed, the model can break in subtle and mysterious ways.
So a Docker container is like a sealed box.
It's a perfect sealed box. It packages your code, your trained model file, and all of its exact library dependencies into a single portable unit. The guarantee is simple. If that container runs on your laptop, it will run exactly the same way on the server, in the cloud, anywhere. It guarantees consistency and eliminates surprises.
Okay, so our model is in its container. We are ready to push the big red button. But the source warns us here, the risk of deployment. How do we update our model? How do we roll out version 2 without crashing the entire system or angering all our users?
This brings us to phase 5, deployment strategies. And you are absolutely right. You don't just overwrite the old model file and cross your fingers. That is amateur hour, and it's incredibly dangerous.
So the source gives us a whole menu of safer strategies. Let's go through them. First, the simplest one. The recreate method, or the Big Bang.
This is exactly what it sounds like. You stop version 1, the service goes down, you start up version 2. It's simple, it's cheap. But the huge downside is that you have downtime during that switch.
Which is unacceptable for many businesses.
For Amazon.com, that's millions of dollars. For some internal back office tool, maybe it's fine. You just tell people it'll be down for 5 minutes.
Okay, so what's a more professional approach? Next up is blue-green deployment.
This is the classic zero downtime strategy. You have your current system running in production. We'll call that blue. It's taking all the live traffic.
Okay.
In parallel, you spin up a complete identical copy of the new system with version 2 of the model. We'll call that green. You can test green as much as you want with fake traffic. Make sure it's stable.
And when you're ready?
When you're confident it works, you go to the router level, the component that directs traffic, and you flip a switch. Instantly, 100% of the live traffic is redirected from blue to green.
And what if green suddenly starts crashing?
You just flip the switch back. Instantly. The rollback is immediate. It's very, very safe. The only downside is cost. For a period of time, you're paying for 2 full production environments, which can be expensive.
Right, you've doubled your server costs. Okay, then we have the canary strategy, like the canary in a coal mine, I assume.
Exactly like that. The idea here is to limit your risk, to limit the blast radius if something goes wrong. Instead of switching all the traffic at once, you send just a small percentage, say 10% to the new model to version 2.
And the other 90% stays on the old, stable version 1.
Correct. And you watch that 10% of traffic like a hawk. You monitor the error rates, the latency. If everything looks good, you slowly dial it up, 20%, 50%, until eventually 100% of the traffic is on the new version. If at any point you see a problem, you can instantly dial it back to 0, and you've only affected a small portion of your users.
That seems incredibly smart. Now, how is that different from the next one, A/B testing? They sound similar.
They do, but they have different goals. A canary deployment is primarily about technical risk. The question is, does it crash? Is it stable? A/B testing is about business impact. The question is, does it work better?
Oh, okay.
You're splitting traffic not just to check for errors, but to measure business metrics. Does Model B generate more revenue per user than Model A? Does it get people to click on more recommended movies? You're running a controlled scientific experiment on your users to see which model is actually more valuable.
That's a crucial distinction. And finally, the source mentions what it calls the safest method of all: shadow deployment. This sounds like something out of a spy movie.
It is the ultimate ninja move of deployment. It's incredibly clever. Here's how it works. Version 1, your current production model, is taking all the real traffic and sending its answers back to the users, just like normal.
Standard stuff.
But in the background, the system also sends a copy of that same live traffic to version 2, the new model. Version 2 processes the request, comes up with an answer, and then throws it away.
It answers silently.
It answers silently.
Yeah.
It writes its prediction to a log file where only the engineers can see it, but its answer never goes to the user.
Why is that so powerful?
Because you get to see exactly how your new model would have performed on real live production traffic without risking a single user interaction. You can compare V1's predictions and V2's predictions side by side on the exact same data. You can prove with 100% certainty that V2 is better or more stable before you ever let it make a single real decision. It is the ultimate safety net.
That is incredibly cool. A full dress rehearsal with a live audience that doesn't even know it's there. Okay, so we've done it. We've deployed. We used a shadow deployment. We verified everything. We did a canary rollout, and now we're live. We're done, right? We can go home.
We are never, ever done.
Yeah.
That is the great illusion of software, but it's especially an illusion in machine learning. This brings us to phase 6, monitoring and maintenance.
The source has a great line here. It says models rot. Software doesn't usually rot. If I write a calculator app, 2 plus 2 will still equal 4 in 10 years. Why is machine learning different? Why do models rot?
Because a calculator app interacts with the fixed, logical rules of mathematics. A machine learning model interacts with the messy, chaotic, constantly changing real world, and the world changes.
So the model, which was a snapshot of the world at one point in time, becomes outdated.
Exactly. The source defines 3 main types of this rot, or, as it's more formally called, drift.
Okay, let's break them down. The first one is data drift.
This is when the statistical properties of the input data change. Imagine you trained a model to predict clothing sales, and you trained it on data from 2019. Your model learned that sales of suits and formal wear were high.
And then 2020 happens.
And then the pandemic happens. Suddenly, people's habits changed overnight. They stopped buying suits and started buying sweatpants. The distribution of the input data, the types of clothes people are buying, has fundamentally shifted. Your model doesn't know about pandemics. It sees this new data and it gets confused. Its predictions will be wrong.
That's a great example. Okay, the second type is concept drift. How is that different?
This is more subtle. This is when the relationship between the data and the answer changes. The input data might look the same, but what it means has changed.
Okay.
Think about our fraud model again. Scammers are always inventing new schemes. A pattern of transactions that was perfectly safe and normal 2 years ago might now be the signature of a new type of fraud. The input data looks similar, but the concept of fraud itself has evolved.
The rules of the game have changed.
The rules of the game have changed, and the model doesn't know it.
And finally, there's model drift.
This is really just the symptom of the other two. Model drift is what you actually measure. The performance of your model, your accuracy, your precision, your recall degrades over time. It used to be 95% accurate, now you're down to 80%. This is the alarm bell that tells you that either data drift or concept drift is happening.
So how do we catch this? We can't just stare at the accuracy number all day. We need tools.
You need dashboards. You need 2 kinds of monitoring. First, there's basic system health. Is the server up? Is the latency okay? For that, you use standard tools like Prometheus and Grafana.
But that won't catch concept drift.
No. For that, you need ML-specific monitoring tools. The source lists several good ones. Evidently AI, Arise AI, Y Labs, Fiddler.
And these tools are designed to look inside the black box.
Yes. They don't just look at the final prediction. They monitor the statistical distributions of all the inputs and outputs. They'll be the ones to raise the alarm and say, hey, the average transaction amount just spiked by 50% this week. That's not normal. You have data drift. They catch the problem before your accuracy plummets.
So when we get that alert, what's the fix? What do we do?
The fix is retraining. You have to take new recent data that reflects the new reality, and you have to train your model again. You have to teach it what the world looks like now.
And the source talks about automated retraining triggers. We don't want a human to have to push a button every time.
Ideally, no. In a mature system, you set up automated rules. If the monitoring tool detects that accuracy has dropped below a certain threshold, say 90%, it should automatically trigger a workflow in Airflow to kick off the retraining pipeline.
Oh, wait. To know the accuracy drop, you have to know what the right answer was. The source calls this the feedback loop, and it sounds like maybe the hardest part of this whole thing.
It is often the hardest part. You need to collect ground truth.
Ground truth.
You predicted the transaction was fraud. Okay.
Yeah.
But was it actually fraud? You might not know for sure until the customer calls the bank a month later to dispute the charge. You predicted a customer was going to churn, did they? You have to wait and see. You have to build systems to collect that ground truth and feed it back into your monitoring and retraining systems. Without that feedback loop, you are flying completely blind.
That is a very sobering thought. Wow. We have covered the entire life cycle. Before we wrap this up, the source has a fantastic architect's cheat sheet section that compares the scale of these architectures.
Yeah.
Because, not everyone is Google or Netflix.
Exactly. And you shouldn't try to be. You'd use the right tool for the job.
So let's do a quick compare and contrast. Small-scale MVP versus a full enterprise big data setup.
Right. If you're a startup just building a minimum viable product, or a small team doing an internal project,
Keep it simple.
keep it incredibly simple. For data engineering, just use pandas and a SQL database. It's fine. For model development, use scikit-learn inside a Jupyter notebook. For deployment, just wrap it in a Flask app and put it on a single virtual machine. And for monitoring, just check the logs every now and then.
Simple, cheap, and fast.
But if you're a large enterprise and you're dealing with terabytes of data and millions of users,
The toolkit changes completely.
completely. Your data engineering is PySpark, Kafka for streaming, and a feature store. Your development is distributed XGBoost with everything meticulously tracked in MLflow. Your deployment is on a massive Kubernetes cluster using a high-performance server like Triton. And your monitoring is a sophisticated suite of tools like Arise AI integrated with Grafana dashboards.
So the key takeaway here really seems to be select the tool based on the criteria. Don't use a sledgehammer to crack a nut.
The source has a great rule of thumb for this. For data size, it says if your data is under, say, 10 gigabytes, Pandas is probably fine. It fits in memory. If it's over that, you need to start looking at a distributed tool like PySpark or Dask. Don't over-engineer. Don't build a massive distributed system when a simple script will do.
So let's try to synthesize all of this. It's been an incredible journey. We started not with code, but by defining the business problem. We moved through the messy, unglamorous reality of data engineering. We did the science experiment, but we did it pragmatically. We deployed it with extreme care, using strategies like shadow mode, and now we're watching it constantly, monitoring it for rot.
It's a complete life cycle.
Yeah.
And what I really hope listeners take away from this is that the code, the algorithm itself, the .fit method, that's maybe 10% of this whole picture.
Maybe.
And the other 90%. The other 90% is the architecture. It's the plumbing, the infrastructure, the testing, the monitoring. It's the system that keeps that little piece of code alive, healthy, and actually useful in the real world.
It really does redefine what it means to build AI. It's not just about being clever. It's about being robust. It's about being an engineer.
Precisely. It's about building a system that can handle change, that can adapt. Because the only thing that is absolutely guaranteed in machine learning is that the world will change, your data will drift, and your model will become wrong if you don't build a life cycle to nurture it.
That's a great place to land, but I have a provocative thought to end on, based on what you just said.
Let's hear it.
We talked about automated monitoring, we talked about automated retraining triggers, and these feedback loops. So if we build a system that can automatically detect when it's drifting, automatically go and grab the new ground truth data, automatically retrain itself on that new data, automatically test itself, and then automatically deploy the new version using a safe canary strategy.
Yeah.
At what point does this system become self-sustaining?
That is the holy grail, isn't it? The true continuous learning loop, the self-healing, self-improving system.
Is it possible?
We are getting closer. The tools are getting there. But there's always a hidden danger. What happens if your feedback loop gets corrupted? What if you start getting bad ground truth data, a bug, or maybe malicious actors are poisoning your data?
So the system would start automatically learning the wrong things.
They would do it very, very fast. It could spiral out of control, automatically deploying worse and worse models, all while thinking it's improving. And that, I think, is why the role of the architect is secure for the foreseeable future.
To be the guardian of the loop.
To be the guardian. You need a human to design the guardrails for the automation. You need a human to step in and ask the common sense question, hold on, is this actually making sense?
So the architect isn't just a builder of the system. In a way, they're the parent of the system.
I like that. The parent of the system, responsible for its growth and well-being.
Well, on that note, I think we are out of time. This has been fantastic. I just want to encourage everyone listening. Take a look at your own projects or the projects you see in your company and ask that question. Are you building a science experiment or are you building a life cycle?
That is the million-dollar question.
Thanks for listening to this deep dive. We'll see you next time.